Chapter 21 deals with electromagnetic induction. We already know that an electric current generates a magnetic field. So Michael Faraday asked the question, well then shouldn't it be possible that somehow we can use a magnetic field to generate electricity? And after a lot of experimentation, they found in fact you can. Most of the electricity we use nowadays, well I guess virtually all of it unless you're using lightning strikes, are generated using electromagnetic induction. So we have three big topics. One is Faraday's law. The second is Lenz's law. And then finally, we're going to spend some time on transformers. As you read through the chapter, the other topic that we're not going to really talk about is inductors and inductance. What they found experimentally is that they could make an electric current if they started with a coil of wire. So suppose we take a coil of wire and we connect it to an ammeter, probably something called a galvanometer, which is a fairly sensitive meter. And of course, normally it would be pointing at 0. So let's suppose there's 0. And if we brought a bar magnet and we just hold it here, absolutely nothing happens. If we put it inside the loop and we hold it there, absolutely nothing happens. But what they found is if we move this magnet so that it's going back into the magnet and then out, and we're moving it back and forth, then our meter would show a current and spike over here. So we can either be moving the bar magnet, or if we prefer, we could move the coil. But when the bar magnet and the coil are in relative motion, we will see an electric current in our meter. Now, we can also do it with an electromagnet. We could take the same coil, hook it up to a meter so that we can see when it's got current. Whoops. And instead of using that bar magnet, we could use a smaller coil that was connected to a battery. Remember, a battery will cause a current to flow. So if this is current flowing, it actually makes a magnetic field very much like that. We have all these magnetic field lines like that of a bar magnet. And if we move it back and forth where it's getting towards and away from that coil, we will also generate a current, cause that needle to move. Okay. This particular example, if we have a battery, we're going to have a constant current, which we have up to now and will continue to represent with a capital I. There is another way to use that electromagnet that won't actually involve having to move it back and forth. The other choice would be simply to take our coil, connect it to our meter so we can see what's going on. And instead of using a battery, what if we used some type of alternating current or some type of dial that we controlled the current? What we would see is we wouldn't need to move this coil up and down or towards and away the magnet. If we have a varying current, now varying currents we use lowercase. If we have a current that varies, that means that magnetic field will vary, and we do not have to actually move the electromagnet towards or away from the coil. Just by varying this current, we change the magnetic field, and that changes the meter. So in each of these cases, what we're seeing is a varying magnetic field through, the pen is trying to mess up on me. Let's try. Okay, my eraser does not want to erase. There we go. So a varying magnetic field through a loop, if you just have one, or a coil, will induce an EMF that's like a battery and a current in the loop or coil. So that's the key to generating electricity. You have to have a varying magnetic field inside a continuous loop or a coil that forms a continuous loop of wire. All of the above actions vary the magnetic flux through the coil. Now, we have not talked about magnetic flux. This is a new idea, but magnetic flux is very similar to electric flux, and we talked about electric flux when we talked about Gauss's law. So let's move on to our next section. This is section 21.2, and it is about magnetic flux. We're going to define it mathematically. The symbol for magnetic flux is a capital Phi. We put a B for magnetic. For electric flux, we would put an E. And it's equal to the perpendicular component of the magnetic field times an area. So what part of the magnetic field is perpendicular to this area? We usually use the formula B A cosine phi. So that B cosine phi gives us that perpendicular component. We know that B is the magnetic field strength, and we measure that in Tesla. A is some area that we have selected. Areas have to be in meters squared. And here's the important part. Phi is the angle between the magnetic field and a normal to the area. We can think of that normal as being a vector representing the direction of the area. We don't really think of area having a direction. So let's look at what that might look like. So let's suppose we've got a magnetic field It's uniform. It points directly to the right. If I have some surface that I put perpendicular to this, then the normal would point in this direction. You can see, let me erase some of this, that these lines of magnetic field lines would sort of just go right through paper. Draw that too perfectly, so they would just all pass right through, like that. That gives us, what I'm going to say is that orientation gives us the maximum flux, because phi is equal to 0 and cosine phi would equal 1. So our flux would just be B times A. Now, if I tilt that a little bit, we can see that fewer lines of force will actually pass through. Some of the lines might miss completely because of the orientation. Some of the lines, we just won't catch as many lines when we lay it down. In this case, we need to use our formula. Our normal would point this way. And our angle phi, if we draw from the common point, there's the direction of B, then phi would be this angle right here. And our flux, we'd have to use the full BA cosine phi. Now, if I take that sheet of paper or that area that I'm visualizing and I lay it down flat, like this, I can see that now the normal points straight up. And actually, none of these magnetic field lines will penetrate. They will all either be directly above it or below it, but they won't pass through it. In this case, phi is equal to 90 degrees because it makes a 90-degree angle with the magnetic field. Cosine phi, of course, cosine 90 is 0, so the flux is 0. There won't be any lines, magnetic lines, passing through that area. Oh, that's from earlier. I didn't erase. When B is perpendicular to the area, which is this first case right here, that's the same thing as saying that B is actually an area I shouldn't put a vector on. That's the same as saying that B is parallel to the normal. That's when we get that maximum flux. We said that the flux would be equal to BA. We can rearrange that and say that B, the magnetic field strength, is equal to the flux divided by the area. When we think of our units, we can see that 1 Tesla is the same as 1 Weber per meter squared. Because of that, sometimes B, which we've been calling the magnetic field strength, is called the flux density. So that would actually be the magnetic flux density because it's giving you the number of Webers per square meter. All right, let's look at an example problem. Example 21.1, and this is straight out of your book. It says we have a plane, which simply means flat, a plane surface, A, that has an area of 3.0 centimeters squared. We're going to need that area in meters squared. To change to meters, you really just have to add a times 10 to the negative 4. And that will give us units of square meters. So the plane surface is placed in a uniform magnetic field. We're going to call that B. Such that B is oriented at an angle of 30 degrees with the surface. Now you're going to have to read these problems very carefully. This does not say that B makes a 30-degree angle with the normal to the surface. It says it makes a 30-degree angle with the surface. So the first question it asks is, what is phi? So we have this magnetic field. We'll draw it uniformly pointing to the right. We know that our surface makes a 30-degree angle. So I'm just going to try to draw this at enough of an angle where that looks like 30 degrees. If I draw the normal, we know a normal makes a 90-degree angle. So in this case, if B is making a 30-degree angle, then the answer to the question is that phi must equal 60 degrees because the angle between B and the normal would be 60 degrees. Second part says, okay, well, if they tell us that the magnetic flux is 0.90 milliwebers, remember milli is 10 to the negative 3, find the magnitude, which just simply means the size, of B. So I'm going to use our formula. I know that the flux is BA cosine phi, which means that B must equal the magnetic flux divided by A cosine phi. So magnetic flux is 0.9 milliwebers, so 0.90 times 10 to the negative 3 Webers. The area is 3.0 times 10 to the negative 4 meters squared. And I have to do that times cosine of 60 degrees. I put that in a calculator. I get that the magnitude I'm not sure why it's not one to say there, but we got that our magnitude B is 6.0 Tesla. It's a pretty strong magnetic field at 6 Tesla. Sorry about this, guys. My computer has been remarkably glitchy lately. Okay. Up the size. Now let's see if I can just move my whiteboard so that I get some fresh space to write on. It's going to let me move it left and right. Doesn't want to let me move it up and down. Okay, well, we'll move sideways since it doesn't want to move up and down. Let's add one more twist to that question. Let's do a part C. Part C says, okay, let's suppose that B is the 6.0 Tesla. We're going to keep that same area, 3.0 times 10 to the negative 4 meters squared. And it says, at what angle is the magnetic flux equal to 0.45 milliwebers? So in other words, at what angle are we going to get half of the flux we had before? So I know I solved this. I'm solving for cosine phi to begin with. So I get cosine phi equals the flux of 0.45 times 10 to the negative 3. And that's the number of Webers. B is 6. And A is 3 times 10 to the negative 4. And I get that cosine phi is actually exactly 0.25. To get the actual angle, I have to say that the angle is the cosine inverse of 0.25. You do want to make sure your calculator is in degrees so we get an answer in degrees when we're working using cosine or cosine inverse. So in this case, phi is 76 degrees. So it's 7, if you rotate it until the normal makes a 76-degree angle with the magnetic field, then you will have the magnetic flux drop to half of its previous value. Okay. Let's see if it's going to let me scroll up this time. Okay, it doesn't like up. There we go. We'll just get clean space. So let's move on to section 21.3. And that's Faraday's law. Faraday's law explains how much EMF you're going to generate. Here's what it says. The magnitude of the induced EMF, which we represent with that cursive E, in a circuit which is that closed loop or that coil, equals the absolute value of the time rate of change of the magnetic flux through the circuit. To say it in symbols, they're telling us that the induced EMF is the absolute value of the change in flux over the change in time. If we were in a calculus-based course, this would of course look like the absolute value of the derivative of the flux per time. We're not in a calculus-based course, so we use this formula. Now keep in mind, the change in flux can be due to several things. It can arise from a change in the magnitude of the magnetic field. In other words, B can be increasing or decreasing. It can be due to a change in the area. If you change the size of that loop, and we'll look at that, it could be increasing or decreasing. Or you could also have a change in the orientation of that loop or that circuit, which of course is phi. If you look at the formula, we know that flux, magnetic flux, is BA cosine phi. So B could be changing, the area could be changing, or cosine phi could be changing. So you're going to have to read those problems and determine what is changing in this problem. And remember, the EMF, that induced EMF, exists as long as the flux is changing. If at some point that flux becomes stable, the current will stop. We have to have it. So if you wanted to maintain a continuous EMF or a continuous current, you have to have a continuously changing magnetic flux through that circuit or through that loop. So let's look at an example. This is example 21.2. And in this case, we're going to have a magnetic field, and we're going to generate it simply like, oops. So there is a south pole of a magnet. Here's our loop. I'm going to keep it very simple, not a coil of wire. We'll just have a single loop. And then we've got the north pole of our magnet. And we know that magnetic field point out of north into south, so we can get a continuous uniform magnetic field. I didn't draw it perfectly. That looks something like this. And the problem says that our magnetic field B is uniform and increasing at 0.020 Teslas per second. So we've got a magnetic field B that is changing with time. Our area, it says, is 120 square centimeters. So I'm going to change that to 120 times 10 to the negative 4 square meters. And the resistance of the loop, which is our little circuit, it's just a loop of wire, is 5 ohms. The problem wants us to find the induced EMF and current. So, induced EMF. We know that the induced EMF is the absolute value of the change in flux per unit time. Oops, it's supposed to be a T. Or the absolute value of the change in BA cosine phi over the change in time. And in this case, this is pretty perfect because look what's changing. It's B. We know that the change in B per unit time is this 0.020. So this simply becomes the 0.020 Tesla per second. That's a change in B over change in time, times the area, 120 times 10 to the negative 4 square meters, times the angle, cosine, in this case 0 degrees, because of course our normal would point straight up in the same direction as the magnetic field. So I put all this in a calculator, and I get that the induced EMF is 2.4 times 10 to the negative 4 volts. Now, if I want to do current, I just use Ohm's law, which tells me that V equals IR, or that the current is equal to the voltage over the resistance. In this case, that's 2.4 times 10 to the negative 4 volts divided by resistance of 5 ohms. And my current comes out to be 4.8 times 10 to the negative 5 amps. That's a pretty straightforward problem, but it's really crucial that when you read the problem, you determine what is changing. In this case, it's the magnetic field strength that's changing. Let's do another one so we can look at something else changing. Really important though, when you're looking at this formula before we do this, if you have a changing flux, you could have a changing magnetic field, or you can have a changing area, or you can have a changing value for cosine phi. So we want to be sure we identify that. Our next example, which is example 21.4, involves something called a slide wire generator. Now, A slide wire generator requires that we have a uniform magnetic field. So I'm going to draw a uniform magnetic field that pretty much just points into the plane of the page. And we have a conductor that's U-shaped, like this. And on top of that conductor, we're going to put a bar, a metal conducting bar. I'm going to draw it dark just so you can see it. Notice that would form a closed loop here. You could see this circle. If we pull this with a particular velocity, then as time goes by, we are going to have the bar at a different location. And that's going to change the size of this area. So we're going to let the distance this way be L. They tell me in this problem that my magnetic field is 0.60 Tesla. It's directed into the page or into the screen. The length of that conducting bar L is 10 centimeters or 0.10 meters. And we're pulling it at a velocity, this is a lowercase v, don't mix it up with voltage, of 2.5 meters per second. So if I look at this as a loop, you can see that the magnetic field is constant and it's not changing with time. You can also see that the length is in fact constant. We don't have phi is not drawn here anywhere, but if we wanted to think about phi would be 0 degrees. Cosine phi, it would also be constant. So what's changing is actually going to be the area in this case. That's going to be the crucial thing. How is the area changing? Well, as this bar moves, if this is the length, then this is our change in width. And the change in the width is equal to V delta T. So we're pulling it at 2.5 meters per second. If we wait 2 seconds, that area will increase by 5 meters. So let's find the induced EMF. It's, of course, the absolute value of that change in flux. In this case, B is constant, so it's going to be B delta A delta T, that's the thing that's changing, cosine phi. Okay. So B is 0.60 Tesla. The area is changing. The area is going to be the length times the change in width. That's going to tell you what the change in area is. That's going to be this part. And of course, phi is 0 degrees, cosine 0 is just 1. So we get 0.60 Tesla times 0.10 times 2.5 meters per second. So this is meters per second. Notice when you multiply that together, that gives you 0.60 Tesla, and this is going to be 0.25 meters squared per second. That's that change in area there that you want to be familiar with. When you put all your numbers in it, you get that the EMF is 0.15 volts. Let me work it the way I worked it in my notes. I worked it a little bit more symbolically in my notes. Let's go back to this idea that E is change in flux per unit time, which in this case would be B, change in area per unit time, cosine phi. Looks just like what we had a minute ago. We know that the change in area would be L times delta W over delta T. That's the change in area. But here's where it gets interesting. This delta W over delta T is simply the speed. That's going to be BLV, and of course cosine phi goes away. So our induced EMF is just BLV. We put in our numbers, 0.60, 0.10, 2.5, and we get that E is equal to 0.15 volts. Okay, so that's Faraday's law, but we haven't talked about, our examples so far involve one loop. Oftentimes what we're going to find is we're going to have multiple loops. In fact, if we have multiple loops, then the induced EMF is just going to be the number of loops times the change in magnetic flux. When we generate electricity at power plants, they generally use these huge coils that are then rotated in magnetic fields. By rotating the coils, they keep the orientation, or that cosine phi, continuously changing. But to get a substantial a substantial EMF, you want to have a lot of loops. You want to have N as big as possible. Let's do one more example, and I'm going to finish this video. This example, we're going to have a circular coil. The shape of that plane area does not matter. And it has a radius of 4 centimeters, which we know is not really what we want. That's going to be R equals 0.04 meters. The coil consists of 500 turns or loops. B is decreasing at negative 0.200 Tesla per second. The negative is just used to indicate a decrease, and the angle phi is 30 degrees. So we read the problem and we see right here the part that's changing is B. That's where our flux is changing. So in this case, E is going to be 500 times the change in flux. Our change in flux is going to be the change in B per unit time times the area, because the area doesn't change, times cosine phi, which does not change. I just put in the positive because I know I have an absolute value. So that's 0.200 Tesla per second. The area, since it is a circular, is going to be pi r squared. And they tell me the angle phi is 30 degrees. If I put that in a calculator, I get an induced EMF of 0.435 volts. Even with 500 turns, that was a fairly small induced voltage. All right, I've kind of touched on this. They're not going to have formulas, and I'm not going to test you about particulars, but you should know what a generator is. Generators are devices that convert mechanical energy into electricity. Most of the time, what you're going to have when you have a generator is you have some type of uniform magnetic field. This magnetic field can be supplied usually by some electromagnets. And in that magnetic field, maybe you have a huge coil of wire. Lots and lots of turns. This thing rotates. And by spinning continuously, the amount of flux that's going through it is continuously changing. Now, depending on how they have the contacts set up, most of the time what you get is an induced EMF, well, I'm drawing kind of crooked, that looks like this with time. It looks sinusoidal. It will go like this, and like this, and like this, and like this. And if you were to draw a picture of the current, try to straighten this out a little bit, this current would also go back, change direction, and look like this. I'm going to use a lowercase I because it is a changing current. Now, notice I want to talk just a little bit. We're not going to do chapter 22, but I want to talk a little bit about while we're doing this alternating current, which is what this is. Notice when the current is positive, it's going in one direction. When it goes negative, it's in another. So each one of these places, the actual current changes direction. If we were to average this current, the average current would be 0, even though we have a continuous current. This is the kind of electricity that's flowing through your home, which isn't really helpful. So what they do instead is they take the current. If you picture this, I'm going to draw a picture of it. And they square the values. Well, if you took all those values and you squared them, you would get bigger graphs, but the negative parts would also be positive. When you square negative, you get a positive. So you get something where the graph now looks like this if you graphed I squared. And then they take the square root of it, and that brings it back to another. So when we talk about alternating current, we usually talk about the value being something called a root mean square. You can think of the root mean square as being the average current, except the true average would be 0. So to make a meaningful value for how much current they have, they square it, which makes it all higher, and then they square root it, and then they average it. I'm sorry, they square it, they average it, then they take the square root. It's the root mean square. You don't really have to know that, but this quantity will always be a positive number. So in problems, if you hear them, when we talk about transformer problems and they say something about the root mean square value of the current, They're just saying the average value of the current is this because we know the actual value of those lowercase currents are continuously changing. Generators are effectively the exact opposite of an electric motor. An electric motor, you put electricity in and you generate mechanical work. With generators, you do mechanical work and you generate electricity. There's different ways to try to rotate these coils, but one of the more, we can use wind, we can use dams and falling water, that's hydroelectric power. Its ideal way is to try to use nature to rotate those coils, whether it's hydroelectric or whether it's wind. And if you rotate those coils continuously in a constant magnetic field, you will generate electricity. All right, I'm going to stop right here. It's more than enough for one sitting. I hope you kind of break these apart when you're listening to them.